In the previous video, we've had a look at the current in a circuit. And we have looked at both the cases of series and parallel connections of resistors. Now in this video, let us have a look at the voltage in a given circuit. So we can imagine voltage as the energy given to a particular number of electrons. So let's say I have a battery here. And again, so in the previous video when we were talking about current, I had given you an analogy of traffic to understand and visualize current. But when we're talking about voltage, there's another analogy that holds that is very useful in understanding and visualizing how voltage and potential difference works. So here we can use the analogy of water and pressure. So when we have a simple circuit, let's say somewhat like this, and a resistor, this can be imagined as a pipe of water pipe. So let's say this battery here is our water pump. So we can imagine this as the pump here that obviously pumps water, and this is our let me just draw it next to this circuit. So let's say I have a pump here that pumps water, and this pump takes the water to some height here. So this is one large pump, let's say, and its job is to take water from the ground level to some particular height. And then we have some pipes that travel parallel to the ground, and then let's say I have some section of pipe that goes down. It reduces the height of the water, and then we have another section of pipe that again travels back to the pump and parallel to the ground, and again from here it simply enters the pump. Yeah, so we have two loops here, and let us just connect the two, or rather I think I should just draw it in this way. Let me just draw it like that. It will make more sense this way. Yeah, so I have the pipe and the circuit here, and let us just compare both of them. So what happens is, I'll not get into the details of it, but we can visualize this as the battery giving potential energy to the electrons. So at this terminal, which is equivalent to this end of the pump, the electrons are given some so I'm talking about positive current, which is the opposite of actual current. So I'll just take the conventional current here. So here the current or the electrons are given some potential energy, just like water. When water enters the pump from this direction, the water is raised to some height, giving it some potential energy given by mgh. I hope you remember that. So the pump gives the water some potential energy here. Similarly, the electrons are given some potential energy by the battery. So let's say this is a 2-volt battery. Let's say it's a 3-volt battery. So every coulomb of charge in this at this terminal is given 3 joules of energy, right? That is what voltage means. Energy per coulomb, joules per coulomb. So if you have 3-volt battery, every coulomb of charge at this point is given a potential energy of 3 joules. So as it moves to the other terminal, it is given 3 joules of energy for every coulomb. And similarly here the water is raised to this height and it is given some potential energy. Now water can travel in this pipe that is parallel to the ground from this end to that end, but in doing so it is only covering some distance. It is not losing any potential energy. Why? Because the height is the same. So if water moves from this end to that end, h doesn't change. So as height does not change, the potential energy does not change. Similarly, this wire that connects this terminal to the resistor itself, it only acts as a medium for the charges to move from this terminal to the resistor. It does not reduce the potential energy of the electrons. It does not take the energy of the electrons. I mean, obviously I'm talking about the ideal conditions where we have no resistance in the wires, and we have the only resistance is offered by the resistor itself, and these wires have zero resistance. For now I'm just assuming it. So no energy is lost as the charges travel through this wire, which is similar to this pipe that is parallel to the ground where no potential energy is dropped. As soon as the water reaches at this end, water starts moving downwards and as it moves downwards, as it covers this section of the pipe, it loses energy. And how much energy does it lose? Well, it loses mgh amount of energy, which is the amount of potential energy it gains. And how is that energy dissipated? Well, that turns into the kinetic energy of water. Similarly here, as the charges reach this point and they travel through the resistor, they begin to lose the energy due to collisions and all that. That is what produces resistance, right? Collisions. And during those collisions, they obviously the velocity of the electrons cannot change, just as here the speed of water cannot change. Why? Because if the water speeds up here, then because the amount of water that is entering the pipe from one end has to be equal to the amount of water exiting the pipe, and so obviously the speed at which the water enters from one end has to be equal to the speed at which water exits the pipe, right? That is logical. And similarly here, the amount of current entering the resistor has to be equal to the amount of current exiting the resistor, because current has nowhere else to go. And yeah, so the speed of the electrons does not change, but the electrons have to dissipate some energy and during those collisions, and that is what causes the heating of resistors. So that is the heating effect of current, and electrons release that energy as heat and maybe sometimes light. And as they reach here, they've lost all the energy that they had, which is 3 joules per coulomb or 3 volts of energy, and then they simply travel back to the battery. Just like here, as soon as water reaches here, it has lost all its potential energy because it's reached the ground level, and it simply travels back to the pump. And here it does not lose or gain any energy, it simply just travels from this end to that end. Similarly, this section of wire just connects this end of the resistor to this terminal of the battery, and no energy is gained or lost in this section here. It only connects the resistor to the battery, and all the potential energy has been lost here, which is equal to 3 volts. So we say that there was a drop in potential of 3 volts across the resistor. Now if we just have a look at this case, we can have one large pipe that across which all the energy is lost. Or what we can do is, let's say I remove this section of the pipe. Let me just shift the diagram slightly. Yeah, so I can have this section of the pipe, and let's say I have some pipe that is parallel to the ground, and then I have again another section of the pipe that goes down, and yeah, I can have this kind of an arrangement. But an equivalent diagram of this in terms of electricity would be again a battery here, which is equivalent to the pump, are wires. And this time, instead of having one resistor, I can have one resistor here and another resistor here, and back to the circuit. So now obviously these two pipes can have different lengths, just like these two resistors can have different resistances. But one thing to be noticed here is that, so if this is a 3 volt battery, and let's say this pump gives the water some energy, mgh, let's say that is, or let's just call it mgh, and just for example, let's say it's 3 joules for every liter of water. For now, let's just call that. So every 3 joules for every liter of water this pump provides. Now as water travels here, it does not lose any energy. As it travels here, it does drop, so the height of the water drops, of the water column, and so does the potential energy. So it loses some potential energy here. Again, in this section, it does not lose any potential energy, because no height is reduced. Again, in this section, the water reduces some potential energy, loses some potential energy because the height is being reduced. But if we look here, the net difference in height is this much, which is equivalent to the previous case, and that has to be equal to the potential energy that the water gains in this pump, right? Because mgh, so m and g are constants, but the height gained through the pump is this much, and that is the change in height back when the water drops from this point to this point. And it doesn't matter if it comes in one large chunk, like if we have only one large pipe here, or we can have two smaller pipes connected by this pipe here. It doesn't matter. The main thing to focus here is that the total drop in potential will be mgh, which is equal to the energy gained here, and that will be equal to the energy that it loses in this section plus the energy it loses in this section. Similarly here, if every coulomb of charge gains a potential energy, gains an energy of, let's say, potential energy of 3 joules, it has to lose those 3 joules in the whole circuit. But here there's no resistance, so it simply flows without any resistance. But here it loses some potential energy, and again it travels to this section without any loss of energy because it's a plain wire. Then again in the next resistor it loses some potential energy, just like water loses potential energy in this section. And the main thing to notice here is that the potential energy lost in this resistor plus the potential energy lost in this section in this resistor has to be equal to 3 volts. Just like the potential energy dropped in this section plus the potential energy dropped in this section has to be equal to the energy gained in this section by the pump. And here, because 3 joules was gained in this at this point, it has to lose that energy in these 2 resistors. Now the amount of the ratio in which it loses those potential energy depends on the resistances of the 2 resistors that you can use Ohm's law to figure out. But the basic idea here is that, let's say, if it loses, the potential drop across this resistor is, let's say, V1, and the potential drop across this resistor is V2, then what we can say is that 3 volts equals V1 plus V2, or if this is, let's just call it V, or the V of the battery. So we can say that V, which is the voltage of the battery, equals to the potential, or it can continue further if you have more resistors. But in a given loop, the total energy that is lost should be equal to the total energy gained, right? Only then it will have 0 potential energy at this point, right? And yeah, so that's it. And if I shift this V from here to that side, so here I have plus V, it will go that side and it will become minus V. That's clear. Yeah, so if I shift it to that side, it becomes minus V there. I'm left with 0 here, and what you can see is that the total potential energy gained by an electron in a whole loop, in any given loop in fact, is 0. That's very simple. So here it gains some energy and then it loses that same amount of energy. It could be in one large chunk, like across one single resistor, or it could be in small pieces, like it loses some energy at the first resistor and some energy at the second resistor, and so on and so forth. But the total energy gained by the electron or any given charge has to be equal to the energy that it loses, and so the net potential energy gained by an electron has to be 0 in any given loop. Now it could be a simple loop like this one, or let's just know that part, or even if I have a parallel connection like this one of 2 resistors, and the resistances could be anything. But the main thing to notice here is that if we take any given loop, let's say I'm taking this loop here, I can just call that A, B, C, D. So the total potential and net potential energy gained has to be 0, which means if it gains a potential energy of, every coulomb gains a potential energy of V joules, then it has to lose that energy in, let's say, if some electron goes in this loop, let's say it goes from A to B to C to D back to A, then it has to lose that same amount of energy that it gained here. And even if it goes through the second loop, let's say it moves from here to here to let's say this point E to F and back to A, let's say it moves in this loop, even then it will have to if it gains this amount of V amount of energy for every coulomb, then that coulomb of charge has to lose that amount of energy as it moves back to the starting point. And yeah, again, that person, Mr. Kirchhoff, so this is a very common sense thing, right? I have explained the basic logic behind it, and he simply called his second rule, or Kirchhoff's loop rule, which simply says that the total potential, the net potential energy gained by any amount of charge in any given loop, in any closed loop actually, has to be 0. So we can just write that in this form, in the form of an equation. But the logic behind is that if some amount of charge gains some amount of potential energy here or anywhere, it has to lose that same amount of potential energy in the remaining circuit. And yeah, obviously one last thing to note here is that if we are talking about the potential difference, so you might have studied in class 10 about the potential, that the potential difference across two resistors connected in parallel connections has to be equal. Why is that so? Well, what is potential? Potential is the ability to do work, and it only depends on the point at which you are. So let's say if we have some electron here, and it has to either move through this resistor and reach here, or it has to move through this resistor and reach here, the energy or the potential energy of this electron only depends on its location. So it doesn't matter if it goes through this path or it moves through this path. If the end point at which it reaches is the same, the potential energy lost by that electron has to be the same. And again, we've also seen that every coulomb of charge has to lose an equal amount of energy that it gained by the battery. So if this is a 3-volt battery, let's say, so it has to lose those 3 volts, and it doesn't matter if it moves through this section of the circuit, it has to lose those 3 joules of energy for every coulomb. And even if it moves to that section of the circuit, it has to lose those 3 joules of energy. And that's a simple reason behind the potential difference between across two resistors that are connected in parallel, in a parallel arrangement, has to be equal. So yeah, that's it for this video.